Good evening, everybody. I hope that I am live. If there's somebody in the chat section, please let me know whether I'm audible or not. Alright, then let's just wait for a minute and then I'll start off with the session. Okay, cool then. So, should we start or should we wait some moment more? I think we can start now. It's already about 6:09. So let's get back to the presentation. Yeah, so I'll probably start now. The people who will join in, they can join in whenever they want. All right. Yeah, Mohammad Sabiullah. Okay, cool. Then I'll start now. So yes, good evening again to everybody who has joined in. Welcome back to Geeks for Geeks Computer Science channel. My name is Praddyumn Shukla, and over here I'm taking live sessions on theory of computation. And in this week particularly, I have been discussing GATE previous year questions on theory of computation. So continuing with that, till now I had talked about finite automata, the questions on finite automata. Then I have also done the questions on regular languages. I also discussed about the questions on context free languages. So today it is going to be more about decidability, undecidability, and all those properties, okay, and countability. And I'll explain a few more concepts within, like it will be kind of like a concept through question kind of session. Okay, so without much ado, let's start off with the session. And before starting off, I want to like explain the last question of yesterday, which was not really when I watched the session. After completing the session, when I watched it, I thought that I should explain this question once again. So I'll be explaining that question once again. And here's that question. So the question says that given the following state table of a finite state machine, FSM basically means finite state machine, there are two states, A and B, one input and one output. Alright, and this is the finite state machine table which is given to you. This is the state table. This is telling me that currently which is the present state. So basically you have two states which is going to define one particular state. Basically you have A and B, and both of these together will define one state. Okay, and one more thing, that you also have the output associated over here, right? So either it is kind of like a Mealy or a Murray machine. You can assume that because Mealy and Murray machines are the in case of Mealy machine, the like you have the finite automata with output, and they are Mealy and Murray machines. So basically over here, whenever you will give the input, let's suppose the current state is A equals to 0 and B equals to 0, and you give the input as 0, then the next state is again going to be 0 comma 0, and its output will be 1. So basically on the transitions, on the basis of the transition, the output is decided. Okay, that if you are seeing 0, then you will print the output as 1, or if you are seeing 1, then you will print the output as 0, depending on where you are currently. All right, now the question is that if the initial state is A equals to 0 and B equals to 0, then what is the minimum length of an input string which will take the machine to the state a equals to 0, b equals to 1 with output as 1. Alright, so basically you are currently on the state a equals to 0 and b equals to 0. Let me write as 0 0 only, so that I probably assume that you will understand that this is a equals to 0 and b equals to 0, and you want to reach a state where a is 0 and b is 1 and the output is 1. So every like you have the output associated with the state. Okay, so now let's first figure out which are the reachable states, and how you will figure that out. You will see the next states which you are going to go. Okay, so currently, like let's suppose you are on this state 0 0 and you are seeing the input as 0, then you are going to go to, again you are going to go to 0 0. Okay, 0 and 0. Similarly, if let's suppose you are on 1 1, this is the input state, and if you see an input symbol as 0, then you are going to a state 1 0. Okay, so why are we checking this? Because my approach would be to create a machine, not machine, I would try to create an automata, and just by seeing the transitions I will figure out that how many minimum length, what is the minimum length of the string which I will require from moving from one state to some other state. Okay, so basically I need to know that which are the reachable states, because if a state is not reachable, then there is no use of having it in my finite automata. Okay, so basically I will just check what are the possible which states I can reach. So if you see closely, just have a look at this next state A and next state B. All right, so now over here you have 0 0. Okay, let me just clear this out, everything over here. I'll explain it again. So you have 0 0. Okay, so you have a state 0 0, and on that, on seeing this input 0, you are going, like you are on some state. I'm not just talking about the input state right now, but when you are seeing some input, then you are going to go to a state 0 0 where the output is going to be 1. Okay, so 0 0 has an output 1. Okay, let's see if some other 0 0 is present. Yes, so 0 0 is present over here also, and here also the output is 1. So for every state there will be associated some output, and again a 0 0, I know that I have again an output as 1. So basically 0 0 state is associated with the output 1. Okay, similarly I will check for all the states, and I will see which output is possible. Okay, now let's see, the next state is 1 0. The next state is 1 0. Do I have any more 1 0? Yes, I have over here. So 1 0 is producing the output of 0, and over here also this 1 0 and this 1 0. In both these cases you are producing the output as 0, right? So 1 0 will produce the output as 0. Now which is the remaining state? It is 0 1, this one 0 1, and again a 0 1, this one, and also a 0 1, this one. So 0 1 is present. So basically 0 1 is producing which outputs? It is producing 0, and then 0 1 is producing 0, and it is again producing 1. So 0 1 is a state which is producing two outputs, right? It is producing 0 as well as it is producing 1. So I will have two states for 0 1. One state will be like this 0 1 slash 0, which is telling me that 0 1 with an output 0, and the other state will be 0 1 slash 1. Okay, so I hope you got this understanding that how I figured out which state is producing which output. I am just checking the output and I am checking the next state which is possible. Okay, that on going to the next state which is the output I am producing. Alright, so let me remove all of this. So basically I will have 4 states in my finite automata. These are the reachable states, right? These are the reachable states. I can reach to them from the initial state, right? So basically now let me draw the automata it will have something like 0 0 and 1 is the output for this. Then I have a state, let me remove all of this. Then I have a state 1 0 1 0 and the output is 0, right? And then I have a state 0 1. So for 0 1 I will have two separate states. One will be 0 1 0 and the other one will be 0 1 slash 1. Okay, after the slash whatever is present, it is telling me the output of that state. Okay, now nothing more is left. I just have to check the like what is actually happening in the table. Just have to look at the table, and on the basis of that I will make the transitions. So now let's start. So 0 0 is our initial state. Okay, this is said over here that a equals to 0 and b equals to 0 is our initial state. Alright, so a equals to 0 0, it will be our initial state. When I am seeing the input as 0, I am going to the next state a equals to 0 0 and the output is 1. So if I am seeing the input as 0, I am going to go to 0 0 and the output is 1. Now let's check this state. Similarly, I'll go step by step. Now when I am on 0 1 and I am seeing the input as 0, then I am going to a state 1 0 where the output is 0. Okay, so 1 0, I know that 1 0 has an output of 0. So from both these 0 1 state, okay, let me draw it properly. So from both these 0 1 states, whenever I will see the input of 0, I will move to the state 1 0. Okay, so if I see a 0 as an input from any of these states, it's not mentioned that from which 0 1 state I have to go. From any of these states, on seeing a 0, I will move to 1 0. Okay, now let's have a look at the third row. This is the third row. So now my present state is 1 0 and on seeing a 0, I am going to 0 1, but remember that the output is 0. So I will go to this state, not this state. Okay, so keep this thing in mind that when you are current state is 1 0, I am seeing the input as 0. So on seeing the input as 0, I am going to this state. Okay, now let's have a look at this row. So this is 1 1 and I do not have 1 1 as the reachable state. So I do not need to draw it because the state which is not reachable, why should I worry about it? Okay, so now this row is 0 0. So on seeing 1, I am going to 0 1 with the output as 0. Okay, so on seeing a 0, on seeing a 1, I am going to 0 1 with the output as 0. Okay, so I am not going to go to this state because this state has output as 1. I want the output as 0. So this will be my state. Okay, now we will see this row. So when I am on 0 1 and I see the input as 1, I go to the state 0 0 and the output is 1. Output is definitely 1 because I have drawn over here that 0 0 has the output as 1, right? So when I am on 0 1, when I see a 1, I am going to go to 0 0. So whenever I will see a 1, I will move from here to here. Let me draw it properly. So from any of these 0 1s, I will go to 0 0 0 only, and one more 1 will be here, this. Okay, now let's see this 1 0. On seeing an input as 1, I am going to the state 0 1 with the output as 1, and this is my final state, right, where I want to reach, because this is my target state, a equals to 0, b equals to 0 with the output as 1, right? So this is my target state. And now let me remove the previous one so that it does not confuse you. So currently I will be on 1 0 and on seeing the input as 1, I am going to the state 0 1, right, with the output as 1, and this is my final state. So on seeing on 1 0, when I will see a 1, I will see a 1. Okay, so I will move to 0 1. Now let's check. I wanted to move from this state, this was my initial state, and I wanted to move from here to here, this state, right? Why 1 1 is not reachable? Yes, it's a very good question. 1 1 is not reachable because in this row, just check out these two columns. Okay, in these two columns, you do not have any row where 1 1 is present. And what is this column telling me? These are the next states. Okay, so if I am just checking that if on seeing some input where I am going, so if I am not able to go to 1 1, there is no next state of 1 1. You see 0 0 is there, 1 0 is there, 0 1 is there, but 1 1 is not present. You can check all the rows. So 1 1 is not present. If it is not present, that means that I am not going to 1 1. Does not matter on which. Let's suppose I am on some state, then on seeing 0 or 1, if I am not able to reach this state 1 1, there is no row where through which I can reach to 1 1. So that means this state is not reachable because it is not present in this next state column, right? I hope this clears your query. So now let's get back to the question. We were on 0 0. I have already seen that the output as 1. So I want to reach from 0 0 to 0 1, right? So which is the minimum length of string which you can have? This on seeing 1, let me remove this. Yeah, just a moment. Yes, okay. So on seeing this one, I will let I see the first symbol as 1. I move from 0 0 to 0 1. Okay, now on seeing now I am on 0 1, this state. Then on seeing a 0, I am moving to 1 0 on, and this is 0, right? 0 1 slash 0. Okay, let me write over here only. So currently I am on 0 0 where the output is 1. Then on seeing a 1, I am going to 0 1 where the output is 0. Then the next thing I see is a 0. So on seeing a 0, I move to the state 1 0 where the output is 0. And then on seeing this 1 over here, right over here, it's very kind of like inside, but I hope you get that. So on seeing a 1, I move finally to this transition over here. I move to 0 1 with the output as 1. Okay, so what all things I saw? I saw 1 0 1. So I saw 1 0 1. I was on this initial state 0 0, and on seeing the input symbol as 1 0 1, I move to this my final state. Let me remove like this. So this is my final state, right? So what is the length of this minimum string? It is 1 0 1. Okay, so the length of this minimum string is 1 0 1. So therefore 3 will be the correct answer. I hope you got this. If you have any doubt, please let me know. What I did, simply I'll recap everything what I did. So basically I just scanned all the next states, and then I got to know which are the reachable states. Okay, if I am able to reach to a next state, some state is present in the next state, then that means that I am able to reach to that state, because this row is telling me that on seeing something I am going to the next state. This state is my next state. Okay, so I got all the reachable states. I try to draw the automata on the basis of all these rows which is given in the finite state machine, and I just ignored 1 1 because I do not have to care about the transitions which are happening in 1 1 because that is not reachable. Okay, and then I just started scanning, I just started traversing from the initial state which was 0 0. I just tried to I want to move to this final state in the minimum number of steps. Okay, option 1, 3 inputs. Yes, that's correct. Not 3 inputs. The input is 1 0 1 and the length of this input is 3. Okay, they are asking me what is the minimum length of an input string. Okay, so the input is not 3, the length of the input is 3. Okay, so 3 is the correct answer. Now let's move on to the next question. Now the next question, this question says that let a less than or equal to m be. So this is an expression. It is denoting me that the language A is mapping reducible, or you can say that many to one reducible to language B. Okay, so basically this this language A, let's suppose I have a language A, that means I can reduce it to a language B. Alright, this is the whole meaning of this expression, A less than equal to M and B. Okay, this is the meaning of this expression. Now the question is that which one of the following options is false? Alright, so what does this mean? So if I say that I am able to reduce this language to a language B and A is less than equal to B, this means that B is at least as hard as A. Right, I hope you understand this point. If I say that B is at least as hard as A, that means, let's suppose let me break it down in this way. What are the options which I have? A and B. If I say that B is at least as hard as A, so if B is hard, then A definitely has to be hard. No, sorry. If A is hard, then B definitely has to be hard. Okay. And similarly, if B is easy, either it can be, a problem can be, let's suppose I have this problem, so either it can be easy or it can be hard. Only these two questions, like these two conditions I am considering. Okay, I'm just trying to explain you the logic what is happening over here. So if A is easy, I can definitely say if B is easy, then I can definitely say that A is also easy, because B is at least as hard as A. So like B cannot be lesser hard than A. At max A can be as hard as B. Okay, so if B is easy, that means A cannot be hard, because I have told that B has to be at least as hard as A. So if B is easy, A cannot be hard, it has to be easy. Okay, now there are two conditions which say that, let's suppose B is hard, then A can be easy or it can be hard, right? It can be easy or it can be hard, because A has to be, it will be always lesser harder than B. So if B is hard, then A can be hard, or it also can be easy. So one condition, this has already been considered, that if B is hard, then A is hard, so A can also be easy, right? Let's suppose A is easy, then you have this condition which I have already discussed and this condition which I have already discussed. So if A is easy, then B can be either easy or hard. Why? Because I told you that B is at least as hard as A. So if A is easy, then B can be harder than A, right? It can be harder than A. B can be harder than A, right? I hope you get this point. So if A is easy, then B can be easy as well as it can be hard. These are the four possibilities which you have, right? Over here, two conditions are very mandatory, that if A is hard, then B is definitely hard. It cannot be easy, because I told you that B has to be as hard, at least as hard as A, right? So the B is definitely hard. Okay, and the second very important point is that if B is easy, then A has to be easy. A has to be easy, right? These are the two mandatory points. Okay, and now let's get back to the options. So this is saying that if B is recursive, then A is also recursive, and I think this is correct. Why? Because if A is recursive, let's suppose I'll just draw the Chomsky hierarchy. So you have regular languages, then you have CFL, then you have CSL, then you have recursive languages. I'll write it in short, and then you have recursively enumerable languages. So I will write recursively enumerable language over here. Okay, this is the Chomsky hierarchy. So if B is recursive, which means B is present over here, then B cannot be then A cannot be harder than B. If I have B over here, then A has to be present inside this boundary only, this boundary. Why? Because A can be as hard as B, it cannot be harder than B. Okay, A can't be harder than B. Okay, so if B is recursive, then A will definitely be recursive. Why? Because A cannot be recursively enumerable. Only harder thing after recursive is recursively enumerable. So if B is recursive, it at max A can be recursive. And whether it is regular language or CFL or CSL, I'm talking about A. If A is regular language or a CFL or a CSL, it is recursive because everything present inside this bracket, this arrow which I told you, this circle, everything present inside it is recursive. All right. So now let me remove this, and okay, I removed this. Let me write it again. Right. Okay, so this option is correct, and I want to check which one of the following is false. So this is correct. So this is true. Okay, let me write it over here. This is true. Now let's see the second option. So the second option says that if A is undecidable, then B is also undecidable, right? If which means that A is hard. Just talk about the harder comparisons of everything. Either a language can be decidable or it can be undecidable, right? So I can say that decidable one is the easier version and undecidable one is the harder version, right? So if I say that A is undecidable, which means that A is hard, then B is definitely hard, right? I have written this point over here, this point important, just check this out. If A is hard, then B is definitely hard. So if A is undecidable, then B will definitely be undecidable. B cannot be decidable because that will make B lesser harder than A. Okay, and that is not correct. Okay, so this is also true. These two first statements are true. Now let's see the third statement. It says that if B is recursively enumerable, then A is also recursively enumerable. That's correct. It's very similar to if B is recursive, then A is recursive, right? Because if I have B over here in this circle, in this inside this circle, this outermost circle, then A will definitely be present inside this like A will definitely be present inside this circle, this outermost circle, right? If B is present inside this circle, then A will also be present inside this circle. So C is also true. Now let's see if D is false or not, right? So if B is not recursively enumerable, which means that B is not recursively enumerable, which means that B is somewhere outside this outer circle, outermost circle, right? Then A is also not recursively enumerable. No, this is false. Why? Because A cannot be. If I say that B is easy, then that does not. If B is hard, then that does not mean that A will also be hard. This is wrong. Because A has to be, it can be lesser or equal harder to B. Okay, A can't be over here I missed this, can't be more harder than B. Okay, this is the only condition. A can't be more harder than B. It can be at least as harder as B, or it can be lesser harder than B. So A can be hard or it can also be easy. So this is wrong. It may or it may not be recursively enumerable, right? If I say that B is present outside this outermost circle, this is the outermost circle, and B is present somewhere over here, then this statement is saying that A will also be present outside this circle. This is wrong. It can be present inside this outermost circle also, right? Because A can be easier than B. So this condition is false, and therefore D will be your correct answer. Okay, I hope you get that. Now A can be recursively enumerable. Yeah, correct. Ankit Anand, hi Ankit. So Mohammed, A can be recursively enumerable. If B is not recursively enumerable, then A can or it cannot be recursively enumerable. Okay, so D statement is false, and you can refer this where this analogy which I just told you, that if A is hard, then B will definitely be hard, and if B is easy, then A has to be easy. Okay. Yeah, good evening Ankit Anand. He joined the session quite late. It's already like 6:40. But anyways, I hope you got this. If you have any doubt, please let me know. All right. Now let's move on to the third question for today. So the third question says that let M denote the encoding of a Turing machine as a string over sigma equals to 0, 1. We know this point, right? Is GFG is bringing paid gate course, Sergi? For now, I can tell you that GFG is launching its test series for GATE 2022, and the enrollments, I think they are out now. You can go on the Geeks4Geeks main website and you can check the test series. And I'm not really sure about the paid GATE course, but because for now we are teaching everything for free on YouTube. So if you are self-preparing, then YouTube is the best option for you. We are over here, we take live sessions over here. Like every subject has almost been covered, so you can check all the other subjects playlists as well. Computer networks and everything is covered, so you can check that as well. Now let's get back to the question without much distraction. Okay, so I am saying that M is the encoding of a Turing machine, and I know that every Turing machine, if I have some Turing machine, then I can encode it into some string, right? I can encode it into some string, right? Great, Sergi, your concepts are awesome. Thank you. Now, I'll just focus on the question now. So the question is that let L is equals to the Turing machines M, where M is a Turing machine that accepts, like L is a set of Turing machines where M is a Turing machine that accepts a string of length 2014. Okay, I could have just confused you. So basically L is a set of Turing machine, and every Turing machine in this set is a Turing machine that accepts a string of length 2014. Okay, and the 2014 is because this question was asked in 2014. So the question is that L is decidable and recursively enumerable, or it is undecidable but recursively enumerable, and all the four options are given to you. Okay, so this question was asked in 2014, and 2014 was a really good paper. I really like the questions which were asked in GATE 2014. So this is one of them. And now let's get back to the question. So basically I can assume that what to assume, it's already mentioned, that M is a Turing machine that accepts a string of length 2014, right? And now L is a language which is a set of M. Okay, so M is a Turing machine, and there can be many such Turing machines. So L is a set of such Turing machines. So I can denote this language L as another Turing machine. Let's suppose I call it M1. Okay, let's call it M1. This M1 is a set of all the Turing machines M, right, which accept a string of length 2014. Okay, so basically M1 is a set of, or you can say M1 is a Turing machine which accepts another Turing machine M. So this is a Turing machine that accepts another Turing machine M. Okay, and I want to check what is this language, whether it is decidable or undecidable, or it is recursive or recursively enumerable. We have to check that. Okay, now one thing to keep in mind is that the length strings of length 2014, they are finite, right? Strings of length 2014, they are finite. So I will give all those strings as input to this Turing machine M. Okay, I say that strings of length 2014 is finite. All the strings, the number of strings of length 2014, they are finite. So Ankit says the option is D. Let's see whether you are correct or not. It might be correct or it might be wrong, but let's see. So basically, this the number of strings of length 2014 is finite. So I will have some finite number of strings of length 2014, and I will give every string as an input to this Turing machine M, right? And now this Turing machine, which is accepting a string of length 2014, it will have two options. Either it will halt. Okay, let me write over here. So let me remove this. So this M, it will either halt and say yes, okay, or it will not halt. It will halt and say yes or no, right? If you give something to the Turing machine, either it is going to halt and it is say yes, I accept this string, or it is going to reject the string, right? And there is another possibility that it does not halt and it goes into an infinite loop, right? These are the two possibilities of M. If I am giving a string of length 2014 to a Turing machine M, then either it can halt or it will say that yes, this string is acceptable or it is not acceptable. And the other possibility is also that it does not halt and it goes on an infinite loop, right? There is this halting problem. If you have not studied about it, I would definitely recommend you to go and study about this problem before solving this question. So halting problem, in brief, I will tell you that halting problem is the problem of telling whether a Turing machine will halt or not. Halt basically means stopping. Okay, so if I am giving some input to the Turing machine, then whether that Turing machine will stop or not, that is the main question of this halting problem. Okay, so now as I told you that either M will halt or it will not halt. Okay, if it is going to halt, it will say that yes, this string is acceptable or it is not acceptable. Now I told you that for this language L, which is a set of such Turing machines M, then I am going to have M1. Is it related to halting problem? Yes, very correct. It is related to halting problem. So M1 is another Turing machine for accepting the language L. And what is L? L is just a set of Turing machine M, set of all M. Okay, so now I will be giving this M as an input to M1. Okay, let me clear the inputs. So where should I write? So yeah, inputs, let me clear. So for M, the input is a string of length 2014, a string, I will write 2014 only. And for M1, M and M1 both are Turing machine, right? So for M1, the input is a Turing machine M itself. Okay, I am going to give a Turing machine M as an input. Why? Because it is written over here that L is a set of Turing machines M, right? M is a Turing machine that accepts a string of length 2014 and L is a set of such Turing machines. So now I am going to give this M as an input to this Turing machine M1, which is representing this language L, right? Now, as I told you that if I will give this M as an input to M1, then either M will halt and it will say that yes or no. Yes, it will say that yes, this string is acceptable, or it will say that no, this string is not acceptable, right? Or the other thing is that it will not halt, M is not going to halt, and it goes into an infinite loop. So correspondingly, M1 on taking the input as M, either M1 will halt when M will halt, and if M does not halt, then M1 will not halt, right? Because if M is not halting, then how will M1 halt, which is taking M as an input, right? So basically, this problem is undecidable. Why? Because I am not able to decide. I cannot tell you whether my M1 is going to halt or not, because M1 is getting the input or Turing machine M, and M may halt or it may not halt, right? And so definitely it is undecidable. Now I have to check whether it is recursively enumerable or not. Okay, so either the correct option will be B or it will be C. Now how to check whether it is recursively enumerable? What are recursively enumerable language first of all? So recursively enumerable languages, you have two types of language. Let me remove all of this so that it is easier for you to understand. So you have two types of languages, right? One is recursive language and the other one is recursively enumerable language. So one is recursive language and the other one is recursively enumerable language, right? So recursive language is accepted by a halting Turing machine, and recursively enumerable language is accepted by the Turing machine may halt or may not halt in case of recursively enumerable language. But in case of recursive language, it will definitely halt and it will tell you whether the string is acceptable or not. But in case of recursively enumerable language, the Turing machine may halt or it may not halt. And this is exactly what is happening over here. M1 may halt if M is halting, or M1 might not halt if M is not halting. M is the input which I am giving to M1. Okay, M is a Turing machine and M1 is also a Turing machine. M is a Turing machine which is given as an input to a separate Turing machine M1. So if M will not halt, then M1 will also not halt, and if M will halt, then M1 will also halt. But we do not know whether it will halt or not. So basically this language is a recursively enumerable language. Why? Because I told you, right, that recursively enumerable languages are accepted by such kind of Turing machines. So this is undecidable, but it is recursively enumerable. So B is the correct answer. Alright, I hope you got this. So Ankit Anand, I don't know whether you just guessed the answer or you solved it, but D is not the correct answer. B will be the correct answer. Okay, if you have any doubt, please let me know. Got my mistake. Thank you. I hope it was clear. Now let's move on to the next question. This was a very interesting question, by the way. Now the question 4, again it was asked in GATE 2014, set 3, right? So now this question is very much property based. It's directly property based, I would say. Why? Because there is a property. Let me first read the question. So let sigma is a finite non-empty alphabet. It is finite. First of all, let's suppose sigma is equals to a comma b. All right, this is the first thing. Now the second thing is that 2 की power kgp year. Yes, not option C, option B will be the correct answer, Mohammed. You can go back to the video and option B will be the correct answer. So yes, this was the kgp year, and I'm not sure whether this was the kgp year or 2013. I'm not really sure about that, or 2015. I'm not sure. Either 2015 or 2014 paper or 2015 paper. Either of these was conducted by IIT Kharagpur. And this year also it is being conducted by IIT Kharagpur, and IIT Kharagpur, as I have already told you in the previous sessions as well, that IIT Kharagpur is known for preparing very good level of questions. Okay, so you can expect that you are going to get a really good question paper this year. Okay, ultimately it does not depend on which IIT is conducting, because ultimately a panel of people sit and they set up the question paper, and this panel may be from that IIT which is for this year. You can say that the panel may have people from IIT Kharagpur, and it will also have some people who will not be of IIT Kharagpur. Okay, so yes, 2013 was from Bombay, so I'm not sure. That's why I told, right, that either 2014 or 2015 that was conducted by IIT Kharagpur. Now let's get back to the question. So basically, which one of the following is true? So sigma is equals to AB and 2 की power sigma star. So this is a power set of sigma star. Okay, what is sigma star? First of all, sigma star, let me tell you, if I have sigma equals to A comma B, then what is sigma star? Sigma star is the set of all the strings possible over a comma b. And what can be those strings? Either it can be epsilon, or it can be a, b, it can also be a b, b a, and so on. It can go on, right? So sigma star is the set of all the possible strings over a comma b. And now 2 की power sigma star, it is also known as the power set. Okay, if I have a set S, then if I have a set S, then or a language S, then 2 की power S is known as the power set of S. Okay, so 2 की power sigma star is the power set of sigma star. Alright, I hope you get this point. Now what is this power set? Okay, so let's suppose if I have sigma equals to a comma b, then 2 की power sigma star will either be like, it will be a subset of this sigma. Okay, not sigma star, I'm explaining the power set of sigma. Okay, sigma and sigma star are different. 2 की power sigma star is different, 2 की power sigma is different. So 2 की power sigma, it is nothing but a subset of this set sigma. Okay, so what are the possible subsets? Either it can be an empty set, right? Either it can be an empty set, or I can have a in the set, or I can have b in the set, or I can have a and both b in the set. This is the power set of sigma. Let me make it again, right? I hope the brackets are pretty clear. Okay, so this is the idea of power set. Okay, now there is straightforward property I can tell you, but I also give you the derivation. So the power set of any set, any infinite set and any uncountable set, it will never be countable. Okay, power set cannot be countable. Now over here, this is countable. Why? Because sigma is finite. Okay, so if a language is infinite, then its power set can never be countable. Okay, what is the meaning of countable and non-countable? Okay, so the countable and non-countable basically means that if I have over here, let's suppose, let me remove this point. Now the question comes up, why is this possible? So I'll give you a brief introduction about the concept, but you can definitely tick the option as 2 की power sigma star is uncountable and sigma star is countable. Now I'll tell you why this is happening. So sigma star is equals to all the possible strings over a comma b, right? So let me write it again. I hope the concept of power set is clear. If I have a set S, then the power set of S will have all the subsets of S. Okay, so now sigma star, it is equal to either epsilon or a or b or a b and so on, right? I hope you get this point. Now this sigma star, every element of this sigma star, every element, it can be mapped to a natural number. And how will I do that? See, the natural number start from 1, 2, 3, so on, right? So 1 can be mapped to epsilon, 2 can be mapped to a, 3 can be mapped to b, and so on. So basically any string which is present in sigma star, let's suppose I have some string over here which is like b a, right? This will go on. Okay, so I have some string b a something, right? Right, so basically this string will be generated in a finite number of steps. Why is that happening? Because I know that this string is of length 5, right? So first I am going to map 1 to the string of length 0, then I will see the length 1 string. So a and b are of length 1, so 2 will be mapped to a and then 3 will be mapped to a. Then similarly a b, then I will have b a b b. So this is 2 length string, so I will map 4, 5, 6, 7 and so on. So basically any string which is present in this sigma star, that will be generated in a finite number of steps, and that is the reason that finite number will be a natural number. It started with 1. Okay, so you can generate epsilon in one step, then A can be generated in 2 steps, then B can be generated in 3 steps, so on. Okay, so basically if you can map every element of a set to a natural number, if you have some pattern, but the set is infinite, then how can we count all the set? It might get unimaginable. See, let me tell you what is actually happening, Ankit. Give me any string of sigma star. It will be some finite length string, right? You will give me a string, give me any string, whether it is, let's suppose, 2000 length string, or let's say the string is of length 3257. Okay, you will give me a finite length string, right? And I know that after a finite number of steps, a string of length 3257 is generated. Why? Because first I generated the string of length 0, which is epsilon. Then in the next steps I generated a strings of length 1, which is A and B. Then I generated the strings of length 2, which is AA, AB, BA, BB, right? So after, like, I am generating a string of length 0, then I am generating the strings of length 1, then I am generating the strings of length 2. So there will be a time when I will generate a string of length 3256, and after that I will generate a string of length 3257, right? So although it is unimaginable, but if you talk on a broader term, the string sigma star will be countable, because you give me any string. Right now over here only, if you give me any string, I can prove that I can generate this string in a finite number of steps, because I have made an approach that I will start from 0 length string, then I will generate 1 length string, then 2 length string. So ultimately whatever string you give me, that the length of that string will be generated. Okay, I'm going step by step. So that is the basic idea. I hope it is clear. So sigma star is countable. Okay, and now 2 की power sigma star is not countable. Why? Let me tell you why is it not countable. So basically you have, let me remove this. What is sigma star? If I say let me draw it over here again. So sigma star is epsilon A, B, AB, and then BA, and so on, right? So what can be the power set of sigma star? This is the diagonalization theorem. It has already been proved that power set is uncountable, but I will explain you very shortly. So what is going to happen is that 2 की power sigma star, which is the power set of sigma star, it will have a subset of this sigma star, right? So let's suppose I can have a subset. Sigma star contains infinite countable strings. Why, sir G? But physically we don't have that much hardware in our computer. For your computer it is not hardable, but we have something called as Turing machine, and that Turing machine, this Turing machine is as equally powerful as your computer. That area is still into research. Let me tell you very interesting thing. Turing machines are a great point of research, and a lot of people do not like research. Even I do not have a lot of interest in research, but I am very interested about this point, which says that till date, today, what is today? Today is 30th June of 2021. Till date, there has not been any computer. You can have any supercomputer or anything like that, but till date there has not been any computer which is as powerful as a Turing machine. Okay, why I have written Turing point? Turing machine. Okay, and therefore you do not have any computer which is as powerful as Turing machine. Everything which a computer can do, that can also be done by a Turing machine. This is the power of a Turing machine. Okay, and that is the reason a lot of research is being going on. A lot of people are trying to generate a computer which can do something that a Turing machine cannot do, right? So this thing over here, generating a string of length 4000, 5000, 10,000, anything you say, that can be definitely done by this Turing machine. It is proven. It is like computer in technical terms, it has been proven, and this area is of great research. Okay, So I hope you get this point, and this a lot of people do not know about this, but if you get to know about this, this is really interesting. Computer science is really amazing. I love computer science. Okay, and this core computer science, if you get deep into it, maybe a lot of people might not understand it, but if you understand it, there are high chances that you will love computer science. Okay, now let's get back to the question. So 2 की power sigma star is the power set of sigma star, right? So what is a power set? It is a subset of the original set. So I can have any subset of this sigma star. Let's suppose I have a subset A as epsilon. Then let's suppose I do not take A and B, I directly take AB. Okay, and then let's suppose I take A and then I take BA. Right? I do not. I skip epsilon. I skip B. I skip AB. I just take A and BA. Okay, this is just a possible power set which I am telling you. Okay, so every element, every set in this power set, I can represent it in a binary string. How? If I will take epsilon, if I will take an element, I will consider it as 1, and if I will not take it, I will consider it as 0. Okay, so let me write it over here. So let's suppose if I have the power in the power set, I told you that I can choose epsilon and I can choose AB, right? So epsilon will be 1, A will be 0, B will be 0, and then AB will be 1, and then BA will be 0, and everything after that will be 0. Right? Let's suppose I choose A and then I choose BA. This is also a subset of this sigma star, right? So in that case, epsilon will be 0, A will be 1 because I have chosen A, then B will be 0, AB will be 0, BA will be 1, 0, and so on, right? Similarly, I can have many power sets, right? So let's suppose I draw something randomly. Let's suppose I draw this thing. Okay, this thing I am going to draw. Okay, this will be basically like it will have epsilon, then it will have B, and it will have something more, maybe it will have BB, and it will have AA, right? This is a possible tabulation form which I am trying to prove. I am trying to tell you about the diagonalization theorem. It is a very interesting theorem. Okay, so I am trying to prove that 2 की power sigma star, the power set, is uncountable. Okay, now in order to prove this, I am going to go with the contradictory method. So contradictory method is that I am going to prove that the opposite of what I am trying to prove. So I will try to assume that okay, 2 की power sigma star is countable. I am trying to assume that it is countable. So if it is countable, then every element which will be in the power set, that is 2 की power sigma star in this set, every element of this set can be encoded in this binary string, right? The binary, what do I say? You can call it a binary code in a string of 0 or 1, right? Every element, I just showed you 3 examples. If I take a power set, like if I take epsilon and AB, then this will be the encoding. If I take A and BA, then this will be the encoding, and so on, right? So basically, I am trying to say that every element of 2 की power sigma star, it can be shown with a binary string of 0 and 1. Now, till now I am assuming that yes, I have like 2 की power sigma star is countable, right? And I am going to map every element to a binary string. Okay. Now, if I take the diagonal of this table, this table will be very, like, it will be very large. But if I take the diagonal of all these elements, the diagonal elements of every row, okay, this will not be this. I will take this row. Okay, let me write to 0 over here. Let me write 1 over here. Okay, so let me remove this part. Now the diagonal will be this diagonal, right? This will be the diagonal. Okay, and I will extract all the elements out of it. So what is the element? I will have 1, 1, 0, and something, so on. Okay, this is the diagonal element which I got. Now if I complement every element of this diagonal element, I will put as 0, 0, 1, and so on. I can prove that this complemented diagonal is not present in this table. Infinite hotel room video, I do not know what Mohammed is saying, but anyways, complemented string, this complemented binary string will not be present in this table which I have just generated. This is the whole table. Okay, this is the whole table. Why? Because the first element is 0. I cannot have 0 because this first element over here, it is 1, right? Similarly, if I have, let's suppose if I have 0 as the first element, let's suppose I go with this element as 0, first element as 0, then the second element cannot be 0, okay, because I have 1 over here. So does not matter how much you try, you will get one element which will not match this diagonal element, because you have taken the complement of every diagonal, right? We have taken the complement of every diagonal element. So the whole element, the string which you will get at some point, let's suppose I have this complemented string is something like this. I have something like this, and then I have 1 0 0 something like this. Okay, so at some point, let's suppose at this point, the diagonal element will be 0, right? The diagonal element will be 0. I hope watch this video, same concept. I hope you get this infinite hotel room video. Okay, you can check that video as well, which Mohammed is suggesting. But my main idea is that this element, this complemented diagonal element, will not be present in the table, because some row, you cannot have any row where the complemented string will have some element which will not match the diagonal element, because the diagonal elements complement, every diagonal element complement is present in this string, right? So therefore you will not have it. And if you have got a string which you do not have in this table, that means that there is some binary string to which you cannot match any element of 2 की power sigma star, right? So therefore 2 की power sigma star is uncountable. This is the diagonalization theorem. I hope it is correct. Ankit, what is the meaning of this YY? I don't understand this YY. Okay, please let me know what it is. So 2 की power sigma star is uncountable and sigma star is countable. Okay, this is the diagonalization theorem. If you want to read more about it, you can go dive deep into, like, you can just Google it and you will get that. But the whole idea is that if you can draw a bigger table and then you will visualize it. Why? Because at some point, let's suppose at third element, let's suppose every element you chose, let's suppose let me explain it once again. So you got this complemented string, right? I'm trying to prove that it is not okay, it is not going to be present in the table. Why? Because let's suppose the complemented string is of length n, okay, then maybe you can get at max n minus 1 elements, as you can get n minus 1 element, but one element will be present which will not match, because I have taken the diagonal elements complement. So you will have one element which will not match the diagonal element in the all the rows. Okay, so I hope you get this point. It's already too late, but now let's get on to the fifth question for today. So this question is directly property based. You have a table for this. Now this by intuition also you can go. The first option is saying that deciding if a given context free grammar is ambiguous or not. So ambiguity is not any kind of thing which you can decide. Why? Because context free grammars are not closed under ambiguity. Context free grammars are not closed under ambiguity. It's not very easy to prove this point. So what you can do is that you can prove that the other three statements are correct. So if they are correct, this will definitely be like the other three statements are decidable. So if they are decidable, then A will definitely be undecidable and A will be your correct answer, right? And how will I prove that B, C, D is decidable? This deciding if a given string B option is generated by a given context free grammar, this is membership algorithm. That whether I'm giving you a string and whether it is being generated by the context free grammar or not, So it is a membership algorithm, and we have a table for it, and this is the table which you have. So under membership algorithm, context-free languages is decidable. This is a decidability table. It is very important, and I'll also show you one more table in the next question. That will be the last question for today. So this decidability table is very important because directly on this table the question is going to come. You can definitely expect one question from either this decidability table or one question from the closure table, which I'll show you in the next question. All right. So basically, the membership problem, under membership problem, CFL is decidable. Then this C option, which says that if the language is empty or not, that is emptiness problem. So under emptiness problem, context free languages is decidable. You can also check for deterministic context free, but if context free is closed under something, then deterministic context free, that is DCFL, will also be closed under it. Okay. Then D option, deciding if the language given by a context free grammar is finite or not, that is finiteness problem, and under finiteness problem also context free languages are decidable. Okay, so under BCD it is decidable. That's for, because of that, A is the wrong option. It is not decidable under. Sir, Telegram channel not found for GFG official. Actually, I'll check about that. I'm not really sure about how it works. Maybe I'll see, and I will give the link in the description the next time in the next session. Okay, but for this question, I hope it is if it is clear to you. Everything is just about the decidability table. You can by heart it because the questions directly come on it. You can also understand it, but it's okay if you just have to by heart it. It's not really bad to by heart something. Okay, now let's move on to the last question for today. Today has been a long session. Now, which one of the following statement is false? Okay, the first is saying that for every non-deterministic Turing machine there exists an equivalent deterministic Turing machine. This is correct. Why? Because non-deterministic Turing machine, every non-deterministic Turing machine, it can be converted into a deterministic Turing machine, and that is the reason non-deterministic Turing machine and deterministic Turing machine, they both are equivalent in power. Okay, the second option says that Turing recognizable languages are closed under union and complementation. Let's have a look at all the options which are given. So now we have to tell which one of the following is false. Which one of the following is false? And now what is Turing recognizable languages? So Turing recognizable languages means a language which can be recognized by a Turing machine. So basically you can just you can assume, you can remember this thing, that Turing recognizable languages are recursively enumerable languages. Anywhere you see Turing recognizable word, then you can definitely say that it is a recursively enumerable language. And Turing decidable languages are recursive languages. Why do I call them as recursive? There is a logic behind it. The logic is that if I am giving you some string, what is decidable? Decidability means that I'm going to give you a string and you have to decide whether that string is present in the language or not. So for that, the Turing machine will halt or it will not halt. This is like decidable languages. For them, the Turing machine will definitely halt because it is decidable, right? It is, by the word it is saying that it is decidable. So if it is decidable, then definitely how it will decide whether it will halt, right? It will halt and it will say that yes, it is present in the string is present in the language, or it is not present in the language. So decidable languages are accepted by halting Turing machines, and which are nothing but recursive language. Okay, and Turing recognizable languages are recursively enumerable language, because every language can be recognized by a Turing machine, and that may halt or may not halt. I can have a language for which the Turing machine will not halt. That is a recursively enumerable language. Okay, but it recognizes the language, so therefore recursively enumerable languages are called Turing recognizable. Okay, now the question boils down to the properties of recursive language and recursively enumerable language, for which you have this closure property table. Over here you can see that recursively enumerable languages, this option sorry, so recursively enumerable languages, they are closed under union and complementation. Let's see, recursively enumerable language, RE, they are closed under union Why? Because it is said that yes, but are they closed under complementation? Are they closed under complementation? Where is my pen, bro? Let me check. Yeah. Are they closed under complementation? No, they are not closed under complementation. So, second statement is false. Let's have a look at the third and fourth statement, whether they are correct or not. So, recursive languages are closed under intersection and complementation. Recursive languages are closed under intersection and complementation. Under complementation, yes. Under intersection, yes. So in both the cases it is it is closed. So third is correct. Now fourth is again Turing recognizable, which means recursively enumerable language. They are closed under union and intersection. So under union, let me remove everything over here. Recursively enumerable language. Okay. Under union, yes, they are closed. Under intersection, yes, they are closed. Okay, so in both they are closed, and therefore yes, I will definitely go and drink water. The session is about to end. So fourth is also correct. So second is not correct. Okay, second is not correct, and therefore second is the false statement, and it will not be correct. Okay, I think this question was asked in GATE 2011 or something. I don't remember. I think it was asked in GATE 2011. You can check it. So with this, I will end up today's session. It was a pretty long session today, but I just wanted to continue because the session was pretty interactive. So please like this session if you understood the concept. If you have any doubt, please drop in the comment box. I will definitely help you. I'll reply with my my account, not with the GFG's account. I will definitely reply. You will get a reply. And please share this session. Please subscribe to the channel if you haven't subscribed. Please share the channel with other friends, because sharing is caring. I personally believe in this. Do not think in this way that okay, this is such a good channel, I should not share it with other people, they will also get benefited. This is a very small mentality. So I personally feel that this is not correct. So just share this session with other friends, share the channel with other friends, ask them to subscribe the channel. And one more thing, remember, GATE 2022 series is launched. You can check it on practice.geeksforgeeks.org. All right, you can check it on this domain, or either you can simply Google GATE 2022 GFG test series. Okay, you can just Google it and you will get the link to the test series. Okay, so you deserve a lot, Sirji. Thanks a lot. How to reach out to you, sir? Mohammed, you can reach out to me on LinkedIn. My name is Praddyumn Shukla, so you can reach out to me on LinkedIn. This is my name. Just search my name, because the spelling of my name is pretty, I hope it is visible, right? This is my name. You can contact me on LinkedIn. If you want me to contact me on Instagram or anything on that, you can also search me on Instagram. But I would prefer, or you can also mail me. If you want me to mail, then I will give you. Other channel gives just a glimpse, but you give clarity. Thank you so much. This means a lot. I hope you will be enjoying the upcoming sessions as well. So with this, I think I'll end up today's session. I'm really thirsty. I really need to drink some water. But it was great having you guys. You guys were really interactive. And with this, I'll end up today's session. Stay home, stay safe. Times are not really good, although COVID is kind of like it is reduced. But I will definitely say that stay safe. Okay, stay home, and thank you. I'll see you in the next session, probably tomorrow. Okay.